Okay. First of all, I would like to thank the organizing committee for giving us the...
Sorry, you can make it full screen, please?
Yes, it is full screen.
No, you can press Ctrl L.
Okay.
Ctrl L, like Los Angeles, L.
Yes, this one.
No. You use, yes, it's perfect. Thank you.
Okay. Is that okay?
Yes, okay. Yes, okay. Please go ahead.
First of all, I would like to thank the organizing committee for giving us the opportunity for attending to this wonderful meeting. I would like to talk about a new generalization of inverse, that is the group inverse of like complex matrices. That is, okay, my talk is has three parts: motivation, introduction, and main results. Okay, the motivation of this study is to establish the representation for the group inverse of a 2x2 black complex matrix as this matrix, where A is an square M by M matrix, B is a rectangular M by N matrix, C is a rectangular N by M matrix, and D is an square N by N matrix. All matrices have complex entries. We establish the necessary and sufficient conditions under which M has group inverse. This is a generalization of inverse that we have before. The explicit representation of M hash, I mean the group inverse of M, in terms of the individual blocks is also given. Okay, if we want to talk about the history of the generalized inverse, maybe we can point out to the more permanent inverse. The study of a generalized inverse of elements in rings and Banach algebras has a rich history. Let X belongs to MNCI means that let X be an squared complex matrix. So in 1955, Penrose established the existence and uniqueness of a matrix like B satisfying this equation, where xt denotes the conjugate transpose of X. The matrix being known as the Penrose inverse, which is a generalized inverse of a matrix X. With some modification of the Penrose inverse, in 1958, Rosin introduced the concept of a new kind of inverse and called it a pseudo-inverse in associative ring and semigroups. Okay, the definition of the pseudo-inverse of Rosin and the group inverse. Let A be a Banach algebra and let A belongs to A. We say that A has Rosin inverse, provided that there exists some B belongs to A such that B is equal to BAB, AB is equal to BA. It means that B commutes with A and A power n is equal to A power n plus 1 multiple to B for some natural number n. The preceding B is unique if it exists, and we denote it by A power B. The smallest n which satisfies the above condition is called the Rosin index of A and is denoted by end of A. If end of A is equal to 1, then B is called the group inverse of A and is denoted by A hash. Okay, to clarify this definition, we use a known theorem from this reference, and this helps us to find a better way to define the group inverse. The theorem is that let A be an algebra with unity and A belongs to this algebra, then the following conditions are equivalent. One, there exists a unique idempotent P such that A plus P is invertible and AP is equal to PA is equal to 0. And the second one is that A has group inverse or A is belonging to A hash. That means that they set up all group invertible elements in an algebra A. We have the definition of group inverse in complex. We say that A has group inverse provided that there exists some square complex matrix X such that this equation holds. Ax is equal to xa, x is equal to xax, and A is equal to axa. Such X is unique and if it exists, and we denote it by A hash. Okay, as the group inverse is a special case of Drazen inverse, and you know that the Drazen inverse has several applications, so the group inverse also has several applications, maybe more than the Drazen inverse. If we want to talk about some applications, we can talk about in system of differential equations, also in Markov chain, in iterative methods, and so on. Most works in the literature concerning representation for the group inverse of partition matrices or black matrices were carried out under certain restriction of their blocks. As it is really a hard problem, there are several works to study this problem. Our work is again about this problem. Now we have the main result. The aim of this section is to establish the representation for the group inverse of the partition complex matrix in terms of individual block A, B, and C, and D. Let A and D have group inverses. A power P and D power P are spectral idempotents of A and D respectively. An expression. A power P is equal to IN minus A hash, and D power P is equal to IN minus D hash. We know the drill. It is one of the main theorem in this talk that introduce how we can compute the group inverse of a black complex matrix. Let A and D have group inverses. If we have this condition, first, B, D power IC is equal to 0 for every non-negative integer number.
I think there is some internet connection problem. Professor Abdolyousefi, can you hear me? Let's wait a couple of minutes, please. Now, Professor Abdolyousefi is not online. We will wait for. Professor Abdolyousefi, can you hear me?
I'm sorry as I have lost the internet. I'm really sorry.
Yeah, don't worry. Please go continue your presentation.
I'm really sorry. Just a moment.
Yes.
Okay, just a moment, please. Is that okay?
Yes, it's okay.
Can I continue?
Sorry, can you make it full screen, please?
Yes, just a moment. Maybe I can start from the main result. Am I right?
Yes, you can start it.
Is that okay?
Yes, it's okay. Thank you.
Okay, I'm really sorry as I have lost the internet. Okay. This is our main result. Our main
I think again, Professor Abdolyousefi having internet trouble problems. So we have to break about 6 minutes for the next session. Thank you for your contribution. See you later. Professor Abdolyousefi, if you present your study in 10 minutes, please continue. Otherwise, sorry, we have to continue with the next section.
I'm sorry. Can you hear me?
Yes, we can hear you. If you present your study in 10 minutes, please continue. Otherwise, we have to continue with the next session.
Okay, I can continue. I hope it is okay. I hope it is okay.
Okay, please go ahead.
Maybe I had better not share my video. Maybe my internet is better. I'm really sorry. Can you hear me?
Yes, we can hear you.
Okay, the main result is about the group inverse of the black complex matrices. The aim of this section is to establish the representation for the group inverse of the black complex matrix M in terms of the individual blacks. Let A power P and D power P are the spectral idempotents of A and D, where A and D have the group inverse. In expression, we have A power P is IN minus A hash, and D power P is equal to IN minus D hash. We know drill. Our main result, one of our main theorem is that let A and D have group inverses. If B, D power IC is equal to 0, then the following are equivalent. First, M has group inverse, and second, we have this equation. A power P, B, D power P is equal to 0. D power P, C, A power P is equal to 0. And CA plus DC multiple to X plus CBD hash plus D power 2Z is equal to 0, where X, Y, and Z are defined in this way. Also in this case, fortunately, we can compute the M hash in this way based on the A hash and D hash. Also, we define X, Y, and Z in this way. By this theorem, we can conclude two corollaries that are the main theorem of two references. One corollary is that let M be this partition matrix. If BC is equal to 0, DC is equal to 0, then the following are equivalent. One, M has group inverse. Second, A power P, B, D power P is equal to 0, and C, A power P is equal to 0, CAX plus CBD hash is equal to 0, where X, Y, and Z are defined in this way. Also in this case, we can compute M hash. This is the main result of a reference, but we can conclude it by our main theorem as a corollary. The other corollary is that let A and D have group inverses. If BC is equal to 0, BD is equal to 0, then the following are equivalent. One, M has group inverse. Second, A power P, B is equal to 0. D power P, C, A, P is equal to 0. C, A hash B plus DC, A hash power 2B plus D power 2Z is equal to 0, where we have X, Y, and Z in this way. Also in this case, we can compute M hash. Now, we come to demonstrate the dual of theorem 1 as following. Let M be a partition matrix. If C, A power A, B is equal to 0 for such I, then the following are equivalent. One, M has group inverse. Second, A power P, B, D power P is equal to 0 and the other conditions where X, Y, and Z are defined as below. Also in this case, we can compute the M hash. Also by this theorem, we can conclude two corollaries, which are the main result of some references, which is first, let M be this partial matrix. If AB is equal to 0, CB is equal to 0, then the following are equivalent. First, M has group inverses, and second, we have this equation. Also, in this case, we can compute M hash. I mean that the group inverse of M. Finally, we give a numerical example to illustrate this theorem, especially theorem 1. This example is that let M be this partition matrix where A, B, D, and C are defined as below. Then M has group inverse, and we can compute M hash. This is our references. Thank you for your attention. I'm really sorry for this problem. Thank you very much for your time and attention. I'm sorry for this problem. I'm in my office and I don't know why the internet is so bad in this time.
Thank you for your presentation, Professor Abdolyousefi. Is there any questions? I think there is no question. Thank you again, Professor Abdolyousefi, for your contribution.